So formally, the theorem to describe variation of parameters. So consider the non-homogeneous differential equation of the form y double prime plus p of x y prime plus q of x y equals some input function g of x with complementary function, that is the solution to the corresponding homogeneous differential equation of the form Cyy1 plus C2y2. All right. So we want a complete solution comprised by some. So the solution would be of the form y equals to y homogeneous, y complementary plus y particular. But in this case, the y particular, which is not a constant times 1 plus another constant times 2, it's those constants are now functions of x or functions of the independent variable, not necessarily x. All right, and we found out that these functions are obtained by evaluating only a couple of integrals. All right, I'm going to box those two integrals that we're going to compute to get the particular solution. Well, all we need is to identify y1 and y2, which we will get by solving the corresponding homogeneous differential equation. In both cases, the numerator of the integrands actually include one of the factors, rather it's that input function. And in both cases, we divide by the Wronskian, which you guys know how to calculate that, right? Okay, so let's have a look at the first example. So number one, solve each differential equation below. Y double prime plus y equals to secant squared. Okay, guys? So finally, we get an example where the input function is something that was forbidden in the previous method of secant squared. Yes, you could argue that you could do this 1 over cosine squared, but still that's a rational function of trigonometric function. So that's still a forbidden function for undetermined coefficients. First of all, let's consider the characteristic equation m squared plus 1 equals to 0. That is m equals plus or minus, m equals to negative 1 or m squared, and m equals to plus or minus the square root of negative 1, which is plus or minus I. Or if you will, 0 plus or minus I. All right? That's because in this case, alpha equals to 0 and beta equals to 1. Be careful, it's not I. Beta is the number that multiplies the imaginary unit. In this case, it's an invisible one. So that means our complementary solution y sub c will be e to the alpha x times c1 cosine beta x plus c2 sine beta x y sub c equals to e to the alpha, which is 0x, times c1 cosine, which is just x, plus c2 sine x. Well, we can reduce this to simply y sub c equals to c1 cosine x plus c2 sine x. So that is a complementary solution. Is what we need to get this complementary solution, because from here we will determine what y1 and y2 are, because for variation of parameters we need to compute the what's it called, the Wronskian. Well, the Wronskian is formed with the first row, which is the set of fundamental solutions and their derivatives depending on the order. All right, so our particular solution y sub p will be of the form u1 y1 plus u2 y sub 2, which in this case is u1, which we don't know what it is, times y1, which we already know what it is, that's cosine x, plus u2 sine x. All right, what do we get from here? So from here we get that y1 again is cosine x and y2 equals sine x. So now we're ready to evaluate the Wronskian, in which in this case it's a Wronskian of order 2. Y sub 1, y sub 2, y sub 1 prime, y sub 2 prime. All right. Okay, so here we go for the matrix. Let's set up the matrix and calculate its determinant. So cosine x, sine x, so the derivative of cosine, which is negative sine x, and the derivative of sine, which is cosine x, and evaluate this 2 by 2 determinant. Well, you guys know how to evaluate 2 by 2 determinants. Well, maybe you already took linear or you're currently taking linear algebra. You already got past that chapter at this point in time, right? Or you did it in college algebra also. So again, or in Calc 3. So the product of the elements along the main diagonal minus the product of the elements along the secondary diagonal. That is cosine times cosine. Is that cosine squared? And then minus negative sine times sine, negative minus negative sine squared x, which is cosine squared x plus sine squared x. What is that equal to? Nice. The Wronskian is 1. Right? Which tells us so at the same time that we have a set of solutions that is linearly independent, right? Because the Wronskian is not equal to 0, right? So we are at the fast food place, right? We got maybe a burger and a drink, or maybe a fry and a drink, or maybe a fry and a burger. So we got we didn't get a multiple of the other, right? So okay, so what now? So now let's evaluate these integrals u1 and u2. Okay, so u1, okay, u1, which is this integral right here, that's the integral of negative y sub 2 g of x. This is supposed to be a g, not a y, right? Little typo here, g of x over w, okay? And so u1 equals to the integral of negative y sub 2 g of x over the Wronskian, just w dx, okay? Which in this case is, what is that? The integral of y2. What's y2 again? Isn't that sine? So negative sine x times g of x. G of x is secant squared. That is the right-hand side of the given differential equation to solve, which is secant squared x, everything divided by the Wronskian, which nicely equals to 1. All right, you want to get some of those, right? Well, depends. Okay, well, let's, at first glance, I don't think there's a way to evaluate this integral by just setting a u substitution or even some integration by parts or any other method. So what I'm going to do here, I will play with the identities, actually. So I'm going to take out the negative. So negative integral of sine x, and I'm going to write this secant, okay? I'm going to write this secant squared as 1 over cosine squared dx, all right? Furthermore, I will break up this cosine squared into, okay, that is negative the integral of sine x times 1. So, do you guys agree cosine squared is the same as cosine times itself? One cosine goes to the denominator of sine, and another cosine remains in the denominator of 1, right? Cosine times cosine times, back to cosine squared. Okay, oh, don't forget the dx. So, all right, this will be equal to, what is that? Sine over cosine? Well, negative integral of tangent x times secant secant. And what's the integral of tangent secant, or the integral of secant tangent? Secant, right? But don't forget the negative, right? Negative secant x. All right? So what about y sub 2? Okay, what about y? Okay, let me actually partially box this one. We're gonna need this for later. That's already, actually, this is already our u1, right? That's already our u1, or we're gonna put everything together at the very end. Okay, what about u2? U2, that's similarly the integral of y1 g of x over the Wronskian w dx. So y1, okay, y1, that was cosine this time, right? That's the integral of cosine x, g of x, which is secant squared, over w, which is simply 1, dx. All right, again, I can set a UDU at this point. However, maybe we can see some reciprocal identities going on between sine and secant, right? However, okay, first of all, that's cosine x times 1 over cosine squared, okay, the x, which is, well, canceling 1 power of cosine with in the denominator with cosine in the numerator, okay? So this will be u2 equals to the integral of dx over cosine. But we can't integrate this cosine while in the denominator. How about move it to the numerator? The integral of secant. What's the integral of secant? Ln of something, right? Yes, ln of secant plus tangent, right? Plus c, right? And guys, we're pretty much done. All right. What does that tell us? So back to y sub p, which we said it was u1 cosine x plus u2 sine x. That is, okay, u1, which is negative secant. Okay, what is that? Negative secant x cosine x. All right. Plus u2, which is, what is that? Ln of absolute value of secant plus tangent times sine x. And it seems like we can do some reductions as well, right? That's because secant and cosine are reciprocal identities. This is equal to 1 times the negative. That's going to give us a negative 1. And actually, okay, let me just rewrite all this. So y sub p will be, let me write the sign in front of the ln, sine x, ln of absolute value of secant x plus tangent x, and I'm going to write the minus 1 at the end. And we're done. All right? We're done. All we do is write down our general solution, which is of the form y equals y sub c plus y sub p, which is what we got from the homogeneous differential equation, c1 cosine x plus c1 sine x, or c1 sine x, c2 cosine, it doesn't matter. For whatever reason, we always write the cosine first in a combination of sines and cosines. Well, not for whatever reason. That's because in a way we go in alphabetic order with the order pairs. These trigonometric functions represents the cosine and the sine, the x coordinate and the y coordinate. Maybe that's why we always write the cosine, but it doesn't matter how you write it. That's up to you. That's sine x ln of secant plus tangent. And don't forget the plus c. So we add, this is the part where this is the moment we write the plus c. Never during anywhere in the process. Oh, wait, no, not plus c. We already have them. C1, C1, C2 here. All right? No additional plus c's. Yes. All right? Yes. It was the negative one from YP. Oh, minus 1. You're right. Yeah, minus 1. You're right. Thank you. Mhm. So guys, as you can see, the process is very algorithmic. It's very formulaic. All you need to do, or you need to know is, of course, I mean, the three different cases for the homogeneous equation, which at this point we have solved many of them. I think you guys already got it. And for that, again, make sure to have your factoring techniques and your integration techniques too when it comes to solving the equations. All right, another y prime plus y prime. Actually, I'm using the same differential equation to save some time. And we already got for y sub c equals to, what was that? C1 cosine x plus C2 sine x. That's actually the same as the as example letter A. All right. If you're curious about how we got it, just rewind the tape and watch example letter A. All right. So let's get the particular solution y sub p equals to u1 y sub 1 u2 y sub 2 equals u1 cosine x plus u2 sine x. Guys, even the Wronskian, it's the same, right? I mean, Wronskian equals to 1 from example. Then again, just refer to the previous example, rewind the tape to that point, and keep going. All right. So let's see what about this. Well, let's just okay, yes, evaluate the integrals, right? Okay. So for the integrals, u1 will be negative the integral of, let me, yeah, I'm going to keep the negative outside. Y sub 2 g of x over the Wronskian dx, right? In this case, well, yes, we have a function of x. If I happen to have a function of t instead, because maybe this differential equation is modeling a situation over time, well, make sure to change the x's to t's, all right? So this will be negative the integral of y sub 2, which is sine, g of x, which is tangent, over 1 dx. Any ideas how to evaluate this integral? A u sub maybe? A u sub, can we do a u sub? Well, the derivative of tangent is not sine, the derivative of sine is not tangent, so let's play with the identities, right? So we know negative integral of sine is sine, and tangent equals sine over cosine, all right? However, this seems to actually making the problem harder than it looks like, because sine squared in the numerator, cosine in the denominator. So we wish we had that cosine in the numerator and do a use of for sine, all right? However, that's not the case. Well, how about a party trick here to turn everything in terms of cosines using trig IDs here? So 1 minus cosine squared over cosine dx. All right. 1 over cosine in the denominator. Oh, this looks like cosecant. Let me actually cosine it. All right. Okay. And that's equal to negative integral of secant x. And what's cosine squared over cosine? Is that a cosine simply? Dx. So what do we have? The integral. We have to, well, do we really need to write this in terms of two integrals? Maybe not really. Maybe the integral of secant, which is, again, ln of secant plus tangent. However, be careful with the negative in front of the integral. All right, that changes the sign of this whole term. Now, what's the integral of cosine? The integral of cosine is sine. But check, we have minus and a minus. Is that a plus? So that keeps it positive. So plus cosine. Wait, sine, right? Sine x. And again, no plus c's in this case, because this is a particular solution. A particular solution doesn't need any c's, all right? Yes. Yes. So the integral of secant, it's a direct formula, ln of secant plus tangent. All right. But because it's a negative in front of the integral, that term goes to negative. And then over here, negative times a negative for the cosine, it's positive. The integral of cosine is positive sign. All right. So careful, it's negative sign when you're differentiating. All right. Yes. This one. Yeah, this is one of those direct formulas. The integral of secant is just this big result, ln of secant plus tangent. And then the integral of cosecant is, I believe, ln of cosecant, I believe, minus cotangent. I forget that one. Right. So, all right. So that's U1. Let's do U2. U2, it's the integral of y sub 1 g of x divided by w dx. All right. Where, what was y1? Wasn't that a cosine? Cosine x, secant, oh wait, not secant, that's tangent over 1 again. But what we have here, oh, this one is going to be nicer because check this out. This is the integral of cosine and tangent, which is sine x over cosine x dx. Boom, cosines go away. And we will simply end up integrating sine. What's the integral of sine? Negative cosine, right? Negative cosine x. All right. So we have everything we need. All right. We have our u1, u2. We already had y1 and y2 from which, again, we took advantage of the same result from the previous example. All right. So y sub p, okay, y sub p, which is u1, y1 plus u2, y2. Okay, this will be okay. U1. What did we get for U1? Oh, we got this humongous quantity here, right? That is negative ln of secant plus tangent plus sine times only y1, which was cosine. Okay, plus u2. What's u2? Negative cosine, actually. Okay, let me do plus negative cosine. Okay, times y2. What was y2? Was that a sine? Sine x? Okay, let's actually reduce this a little bit. Okay, let's see. Well, because you'll see what's gonna happen here. Okay, so I'm going to distribute this negative ln with cosine and this sine with cosine. All right, this will be equal to, okay, I'm gonna write sine cosine first. So sine x cosine x, and then minus this big ln times cosine, okay, minus cosine x, big ln secant x plus tangent x, plus actually minus because plus minus, that makes it a minus sine x cosine x. All right. And well, check, these go away, and our y sub p will actually reduce to simply y sub p equals to, what is that? Negative cosine x ln of secant x plus tangent x. All right. Now we may go ahead and write the general solution to the differential equation. All right. So let's see what about it. So again, y equals to y sub c, that is the complementary solution, the solution out of the homogeneous equation, plus y sub p, which is the particular solution, which is what we just got. What was that? So C1 cosine x plus C2 sine x. And then careful, signs matter, minus cosine x ln of secant x plus tangent x. Final answer. Right. Final answer. There, it seems like there's one more exercise. The next exercise is going to be a little more elaborate. Okay, so buckle up. All right. Okay, so what do we have? Y double prime minus 4y prime plus 4y equals to e to the 2x divided by x squared. Well, at first glance, it seems like this problem could have been solved using undetermined coefficients because of the exponential e to the 2x and because of the quadratic x squared. However, be careful. Unfortunately, that's not the case because this guy right here is really x to the negative 2 e to the 2x. And unfortunately, well, this is either uh, a polynomial, or rather a variable, or an algebraic function with a negative exponent, which is actually forbidden from the undetermined coefficient. So that's why, in this case, we only use the variation of parameters. Okay, so for this one, we have a totally different differential equation. So I cannot just use the result from A and B. So what do we have here? M squared minus 4m plus 4 equals to 0. All right, so let's solve this polynomial equation. Are there any factors of 4 that add up to negative 4? What are they? Mhm. And minus 2. Minus 2, minus 2. What do we have? A repeated case, right? We have repeated. So, I mean, essentially we have one solution, but again, you guys know how to handle repeated solutions. So here, m equals to 2, repeated. All right. Okay. So y sub c equals to c1 e to the 2x plus c2 e to the 2x, however, multiplied by 1 power of x. If we had an equation, again, with m equals to 2 repeated 5 times, then we would need x squared, x to the third, and x to the fourth. So 3 more, right? 3 more powers. All right. So, okay, so y sub p, okay, let's go back to, let's move on to y sub p equals to u1 uh, y1 plus u2 y2, where u1 equals to, u1 times e to the 2x plus u2 x e to the 2x. This means, okay, this means the following. Y1 equals to e to the 2x and y2 equals x e to the 2x. All right? All right. Wronskian first. So the big Wronskian, which is w equals to y sub 1, y sub 2, y sub 1 prime, y sub 2 prime. All right? Okay, so the first row, I hope no problem. All right? So that is e to the 2x, and then x e to the 2x. Well, the derivative of e to the 2x, that'll be 2e to the 2x. However, to differentiate x e to the 2x, what do we need here? Product rule, all right? The derivative of x, which is 1. Okay, actually, you know what? Let me do that differentiation at the top, and then I'm just going to write the result here because I don't want to like write a whole matrix. So x e to the 2x prime, that is 1 times e to the 2x plus the derivative of e to the 2x, which is itself times 2 by mini chain rule times x. So this reduces to e to the 2x simply, and this 2x in front of the exponential. So we need to compute this humongous determinant. Let me actually highlight the entries we're going to multiply together to give you a better visual. So we will multiply e to the 2x with all this madness there, all right? That is e to the, yes, e to the 2x times e to the 2x plus 2x e to the 2x, okay? And then we're going to multiply these other entries here. This entry times this other entry, however, by subtracting. So subtract x e to the 2x times 2 e to the 2x. All right? All right, well, let's simplify this. So e to the 2x times itself, you guys agree this is e to the 4x? And e to the 2x times 2x e to the 2x, so that's simply plus 2x e to the 4x. And then minus x, also actually 2x e to the 4x. Because we have the same base of the exponential, we add the exponents. 2x plus 2x equals to 4x. And even better, actually, these cancel out, right? To give us e to the 4x, right? So again, this Wronskian was not as straightforward as the previous example. It was a little more involved, as I mentioned before, all right? So I believe we have everything ready to evaluate the integrals for the u1, u2, which are the particular solution part of the problem. So u1, that's negative the integral of y sub 2 g of x over the humongous Wronskian. So I believe I'm going to need more space here. So let me move this further down. All right, so that's negative the integral of y sub 2. What's y sub 2? X e to the 2x. What's g of x? Remember this e to the 2x? Well, actually, let me do e to the 2x over x squared. Everything divided by the Wronskian. So e to the 4x. All right? All that with respect x. Yes, the integrand looks crazy, but it's more far than by this one because number one, this is the integral of what is x divided by x squared? Wouldn't that be an x in the denominator? Okay, so this would be x in the denominator. In the numerator, we would end up with e to the 2x times itself, which is e to the 4x divided by e to the 4x in the denominator, which cancel out. All right. And that's end up being the integral of 1 over x dx, which is, don't forget the minus. That's note to myself. Okay. And this is negative ln of x. Well, absolute value of x, right? So that is u1. Similarly, u sub 2 equals the integral of y sub 1 g of x divided by w dx. And again, I think I'm going to need more room here. Okay. What's y sub 1? Y sub 1 was that e to the 2x, so that's the integral of e to the 2x, which is y sub 1, times g of x, which is e to the 2x, also divided by x squared, and everything divided by e to the 4x, which is the Wronskian dx. All right? Okay. Again, actually, there's no excess to simplify or cancel out, so I'm going to rewrite this as the integral of x squared in the denominator e to the 4x, and in the numerator e to the 2x times itself, isn't that e to the 4x, which again divides out. And well, I can't or we can't integrate x squared in the denominator. However, we can use the general power rule with the negative exponent. Well, the integral of x to the negative 2, is that a negative? Is that x? to the negative 2 plus 1 over negative 2 plus 1, which is x to the negative 1 over negative 1, which is negative 1 over x. All right? So two negative results for u1 and u2. All right? And again, we're pretty much done. Right? We just found the functions u1 and u2 that comprise the particular solution, along with, of course, a combination with the results from the homogeneous. All right. So y, okay. So y, which is y sub c plus y sub p, equals to, first of all, c1 e to the 2x plus c2 e to the, x e to the 2x. And then what do we have? Actually, you know what? Hold on. Let me take a step back. Let me save this for later. All right. I needed to write y sub p first because it requires uh, some some simplifications here. So y sub p, which is u1 e to the, well, u1 y1 plus u2 y2. So u1, which is negative ln x times y1, which is e to the 2x, plus u2, what's y2? u2, negative 1 over x times x e to the 2x. Okay, so we need some calculate, some simplifications with the x's here. Also, I believe that's about it. Also, I'd like to write negative e to the 2x ln x plus, or actually minus, e to the 2x, all right? And finally, we may bring all this madness here together to join the party with the general solution, all right? So minus e to the 2x ln x minus e to the 2x, all right? And it seems like we're done. However, be careful, guys. Check this out. Check. What about this guy right here? Do you guys agree these two are duplicates? Because what do we have? C1 minus 1. If we put them together, okay, let me do that on the side with a different color. And guys, because if you put all that on the homework on what's it called? My open math, you may get it wrong. So you want to make sure to simplify all the way because C1 e to the 2x minus e to the 2x. Okay, this is C1 minus 1 e to the 2x. Do you guys agree with this? Factoring the exponential. But hey, that's a constant. We don't know what it is. Minus 1. Isn't that just another constant? So by absorption, this is equal to simply C1 e to the 2x. All right? Back to the final result. This is y equals C1 e to the 2x plus C2x e to the 2x minus the only term that survives is e to the 2x ln of x. And there we go. All right.